All right, class, this is the first notes from 7.1 through 7.3, so that's 7.1, 7.2, and 7.3 sections in the book. They are all copied together in a scan so that, along with this assignment, so you should be able to see all that. So this one is like an extension of Chapter 6, so the periodic properties of the elements. So we're going to talk a lot about electron configurations, a lot about properties of the elements and those properties that are associated with the electron configurations and how that all fits together. So let's take a look at the first part of this. So development of the periodic table, elements in the same group generally have similar chemical properties. We've talked about this before, I believe. Properties are not identical, however, which means that there's a change as you go from the top of the group down to the bottom of the group. So, okay, so let's talk about Dmitri Mendeleev and Lothar Meyer worked independently and came to the same conclusion about how the elements should be grouped. If you take a look here, the blue elements are the ones that have been here, the gray ones are the ones that have been here since ancient time, which includes iron, copper, silver, gold, even mercury, tin, and lead. But the blue ones have been the ones that were discovered, like, I would say, within 100 years of Dmitri Mendeleev and Lothar Meyer. It's like a Bond villain or something ridiculous. So anyway, most of the blue and then the darker gray elements they knew about, and then it was only these that were brand new. Those they knew about, those they knew about, those they knew about. These are the ones discovered afterwards, and these are the ones discovered afterwards here. So this group here was discovered afterwards. Notice that that's not a huge amount on the periodic table. Most of the ones that you are familiar with were known by the time Mendeleev had done his work to create the first periodic table. He did it using atomic masses. So Mendeleev, for instance, predicted the discovery of germanium. He did. Now, if you take a look at this, he used the atomic weights to arrange the elements, but he had holes in his periodic table, and one of the holes was the one that they were looking. He called it eco-silicon because it was below silicon on his periodic table, but there was a hole there, and he didn't know what the name, he didn't know if they would ever discover it, but he knew an element should be there. So he started making predictions about exactly what he thought this element should be like. And as it turns out, he was absolutely very close because of the things that were around germanium. So on either side of germanium, top and bottom, left and right, he started to average those things together and predict what they would be. And it turns out he was absolutely very close, especially on the density of the oxide. So let's move on. So he did some predicting, which was very cool. Periodic trends in this chapter will rationalize observed trends in size of the atoms and ions. We're going to talk about that. Ionization energy is for the next time, and electron affinity is for the next time. So first of all, effective nuclear charge. What is the effective nuclear charge? So you guys know that protons have a plus charge, and for sodium there are 11 plus charges in the very center of the atom, and then those electrons are spread outside the atom, and there are 11 of them. So 11 pluses, 11 minuses, and we don't talk much more about that, but it actually is way more complicated than that. So the combined effect, so the nucleus has a plus 11, and each of the electrons has a minus 1, but there's one on the very outside for sodium. Now that very outside means that it's usually out around here. But notice that it can spend some time a little bit there, and it can spend some time a little bit there. All the other electrons that are outside, that are like part of neon's electron configuration, they're called core electrons. And most of the time, the valence electron that's out here spends its time outside the core electrons, but not always. And because of that, times that it slips back inside within the core electrons, because that happens, remember these are called nodes here, we talked about that before, there's two nodes if it's 3s, then because that electron spends some time inside, its actual effective nuclear charge is going to be, it feels more than just one proton's worth of plus charge. it actually feels closer to 2.5 times the charge because of where its position is. So electrons that sneak inside core electrons feel more of the positive charge from the core. That's what effective nuclear charge is. And that changes the properties of some of these elements. So nuclear charge that an atom experiences depends on both factors, not just that they're opposite charges, but also how far away it is. And don't forget, these core electrons are pushing off, they are repelling the valence electron. So all these factors kind of filter into or kind of make up the effective nuclear charge property. Let's keep moving here. This is kind of, I don't know why it does this. That's not what that should be. It should be Z minus S. Z is the number of plus charges, or the number of protons, which is 11 for sodium. S is the screening constant. Usually it's close to the number of inner electrons, so when you do something like this, you get a +1, except in this case here, the screening is like a little bit closer to an 8.5, which means that we end up with something like a +2.5. And that's how we find the Z elective. You have to know the S, the screening constant, for each element if you're going to find the Z effective, the effective nuclear charge. All right, I'm going to move on. Now let's talk about size of the atoms. So the bonding atomic radius is defined as 1/2 the distance between the covalently bonded nuclei. Nuclei, in this case, you would expect these two to be the same, right? So maybe something like oxygen, where it's O2, or one of those Brinkelhoff. You remember Brinkelhoff, don't you? All of these have a subscript 2 because, like, oxygen likes to exist together, so does bromine, so does iodine, and so on. So what they do is they take the distance from one nuclei to the other, because they can actually measure that, and they cut that in half, and that's called the bonding radius. Okay, most of the time we just use the bonding radius as like the radius because because that's an actual distance they can measure. So notice that the problem is that it gets real fuzzy. It gets real fuzzy as to where the last electron is, and it's always a probability statement anyway. These electrons are moving around so fast we can't even tell where they are, but we get the general idea. So atomic radii, it ends up being, again, another like big-time math problem. So take a look at the size of the atoms. So as we go from left to right on the periodic table, you can see that the periodic table has a pattern to it for the size of the atom, and it decreases as you go from left to right. Now this is odd because students are always like, well, what about the number of electrons? We're adding electrons. Yes, but we're adding electrons into spaces already provided for the electrons to be there. Remember, when you start a new period, like you go from lithium to sodium, you go from period 2 to period 3, we have now set aside places for electrons to fit into as you go all the way across. So the actual atom doesn't get bigger, it actually gets smaller because we're adding plus charges and we're adding negative charges, and they attract each other. So they actually get pulled in as you go across. So the atoms get smaller as you go from left to right. Now there are some anomalies. Some things do like get larger and then smaller again, but for the most part, they all get smaller as you go across. But if we're adding, when you go down a period, we're adding electron shells, like the major energy levels, that increases the size each time. So when you go down a period, like when you go down a group increasing periods, you are increasing the size of the atom, just like you see in my picture here. But as you go from left to right, though, you're filling in those spaces with electrons that are already there, and they're being sucked closer and closer to the nucleus because the pull of the positive on the negative sucks the atom in. So let's make sure you understand it decreases from left to right, but increases from top to bottom. Okay, now take a look at what happens when we talk about the ions. So the ions are different because metals develop a different ion than nonmetals do. Mostly metals develop a cation, which is a positive charge. Okay, so if it's a positive charge and you get rid of one electron, look what happens. You go from 1.34 for lithium to 0.68 with that one electron gone. Okay, and that actually makes sense because you have more protons pulling in those two leftover electrons that are core electrons, so they get sucked in more. So when you lose an electron, your size decreases substantially. But if you gain an electron like you do over here, your size increases because you don't have the protons in the nucleus to offset the more negative charges. And those negative charges on the outside now tend to repel each other, which pushes them even further out. So again, like that's a pretty big difference. The negative ions increase in size, the positive ions decrease in size, and that's the deal. Going down a group still follows the same pattern. You increase no matter what. So that's all that says. So I'm going to keep going through here. Size of the atoms. This says exactly what I just said. I just went through all of this. So cations are smaller than parent atoms. Outermost electrons are removed and repulsions are reduced. Blah, blah, blah. Anions are larger than their parent ions. Electrons are added and repulsions are increased. That's exactly what I said. And size of the ions increase as you go down a column due to increasing value of N, or the major energy level. Okay? And I think that's the end of... isoelectric series, ions that have the same number of electrons. So lithium has a +1, beryllium has a +2, boron has a +3, oxygen has a -2, and fluorine has a -1. These all have the same number of electrons. So as you go across, what happens is the ionic size decreases with increasing nuclear charge. Where are we at here? Ionic size decreases with increasing nuclear charge, and that's what we're looking at. So this is 3 nuclear charges, 4, 5. Yep. This one is not 6, it's 8 and 9. So as you go higher in nuclear charge, where are we at here? Increases, except for the fact that, take a look at this, it's starting to decrease a little bit more here in the negative group. So it goes, where are we at here? So it decreases as we go across. Notice it jumps back up though, because now we've gone from, our ions are now anions instead of cations. So we're not losing electrons here, we're gaining electrons, and that's why it increases. Okay, I think that's it for good. Yes, ionization energy is 7.4. So thank you for paying attention.